In this video, we're going to talk about how to find derivatives of inverse functions. But before we get to derivatives, let's make sure we remember what an inverse function is and how to find it. So for this quick review problem, we're going to graph the line y equals 2x plus 1, and I'm just going to do a quick sketch here. So if it's 2x plus 1, that means that I start at 1 on the y-axis, and I have a slope of 2, which is a rise of 2 and a run of 1, and so forth. And then I'm going to do my best to sketch this line. Alright, so there is the line 2x plus 1. Okay, so my first question is simple. What's the slope, or the rise over run? And for this function, our rise and run was simply the 2 over 1, which is the coefficient of x. And now for a slightly harder question, which is to find the inverse function. So I'm not sure how much we remember about this, but if we start with the equation y equals 2x plus 1, then to find our inverse function, we first have to switch x and y. So where y was, x now is going to be, and vice versa. And then we resolve for this new y value. So I would subtract 1, and then divide by 2 on both sides. And I'm going to go ahead and break it up into two pieces so it looks like an mx plus b. So that would be a 1x over 2, or 1/2 x, minus 1/2 equals y. So we can rewrite that using inverse function notation, which if we remember is the little -1. So the inverse function of x will be 1/2 x minus 1/2. And now we're going to graph that as well. Alright, so on that same graph, it looks like I'm going to have a y-intercept of -1/2 and a rise and a run of 1/2. Okay, so we're going to estimate here. And then a rise of 1, run of 2. Then I'm going to continue that. Alright, let's see if I can sketch this. Alright, so there is my original function, 2x plus 1, and the inverse function, -1/2 x minus 1/2. Alright, so for our next question, I'm just going to ask another pretty simple one, which is what's the slope of the inverse function? And we can see right here in our equation that the slope of the inverse is 1 over 2. And there's a better sketch of this here if you actually use a graphing calculator. Obviously, it's far superior to my drawing. But what I want you guys to notice is, first of all, one thing that hopefully we remember about inverses is that they're symmetrical to the line y equals x. Okay, so that's kind of how we understand that relationship. We switch the x and y. So looking at points for each function, if the point -2, -3 is on the original function, then the reverse of that, -3, -2, is going to be on that inverse function. And so basically if we were to switch all of the x and y's, that's how we get two functions that are symmetrical around that y equals x line. So if the point 2, 5 is on the original line, what point would that correspond to on the inverse function? Okay, so we're saying if 2, 5 again is on the original function, the y equals 2x plus 1, then what point would that be corresponding to on the inverse function? And just again, looking at how our table is laid out here, 2, 5 on the original function would simply give us 5, 2 on the inverse function. Okay, so just to reiterate that relationship, whatever your rise over run, this one would be a change in y over change in x of 2 over 1, that gets switched, okay, and it looks like the reverse of that, the reciprocal of that, okay, and then similar to that, the coordinate point x and y also get switched when you're looking at a function and its inverse. So in summary of this review problem, the slope of the line at 2, 5 on the original function is the reciprocal of the slope of the inverse function at 5, 2. And we're going to use this relationship to do much more complicated problems involving derivatives now. Alright, so these steps are going to be your options for dealing with finding derivatives of inverse functions. And the first two steps really are pretty straightforward. Your first step is just to find a coordinate point of the original function. So a lot of times they only give us x or maybe a y value, but we'll need both of those pieces. We'll need the whole point. So find a point, and I'm just going to say q comma p. Obviously it's the same as xy, but we're just using different letters today. And again, we're going to do that in the original function. And that may require using a calculator for some of the examples we're going to do. Then our second step is to simply find the corresponding point on the inverse function, which hopefully, if you remember what we just reviewed, is basically just p comma q. You just switch them. Alright, from this point on, there's really two methods you can utilize. With method 1, we're going to use implicit differentiation, what we've been working on recently. Alright, so that's going to be our first thing we'll look at. And then, actually, let's just pull this down. Ooh. And then method 2, almost forgot that, is going to be based on that concept that inverse functions have reciprocal slopes from the original functions. So both of these are pretty easy. It's really up to you which method you want to use moving forward, but we're going to do both on the two examples this video covers. So how do we finish the problem with method 1? Well, step 3 would simply be to actually do the step of switching x and y, finding that inverse function, and then deriving it implicitly, with your final step being just plugging in your point xy. So you would isolate that dy dx like we've been practicing, and then substitute in inverse point, since you're working with the inverse function at that part of the step, which if you remember from up here, we're just calling the inverse point p comma q. And then you would be done. With method 2, you kind of avoid the whole finding the actual inverse function, because really what we're going to do with method 2 is find that slope of the original function, and then it's just going to be the reciprocal of that. So remember, to find the slope, we actually take the derivative of the original function. So you're finding that derivative of the original function at the point p comma q, which would basically be f prime of that original x value. Find that derivative at that point. And then the second step would be to find the reciprocal of whatever you get as your answer. Okay, and the fancy way of notating this, which you'll see in our first example here in a minute, it would be the derivative of the inverse function, or the slope of the inverse function at, well, its x value would be the y value of the original function. So at q, oh, Miss Wright made a boo-boo. I was looking over here. This is our inverse point. So our original point would actually be q comma p, my b. Not an important detail at all. Sorry about that. So that would be f prime of q. So the inverse function at p, or at that y value that you originally started with, would just be 1 over whatever that derivative function is, f prime of q. But really, that's just a fancy way of notating it. You're finding the slope at a point, then finding the reciprocal slope. That's all it is. All right, let's do our first example. So let f of x equals 1/4 x cubed plus x minus 1. Find the derivative of the inverse function at 3 using both methods. And the first thing we have to get used to is if this is the input of the inverse function, it means that was the output value or the y value of the original function. So 3 is the y value of the original if it's the x value of the inverse. Okay? So the first thing I need to do is find the point. So we have the y value. Okay, we have something comma 3. We're trying to find that x value. So I'm going to take my original function, set the y equal to 3. And this is not one that I'll make you solve by hand. You're welcome. So we're actually going to go type this in a calculator. And the way you could do this is you could go, like we would break it into two pieces. Y1 would be the left side, Y2 would be the right side, or however you can switch those, doesn't matter. But you're going to type it in as a system, two separate lines, and then find where they cross. And if you did that correctly, you should find that they intersect at the point 2, 3. Okay, so we have the point 2, 3 of our original function. So then we have an inverse of 3, 2 for our inverse function. And I'm going to abbreviate function fn. Okay? Alright, so we found our 2 points. I'll just label this original just to really be clear here. Alright, so now we're going to do both methods. Okay, so method 1, I'm going to do on the left. So with method 1, I need to actually find the inverse function. So I always start by writing the original function, which was 1/4 x cubed plus x minus 1. Okay, so to find the inverse function, I switch x and y. Alright, and then I have to actually do implicit differentiation. Okay, so if we derive x, we simply get 1. If we derive y cubed, remember that's a function, so we'll do the chain rule, and then it's times dy dx. Just regular y becomes dy dx, and that minus 1 simply goes to 0. So now I'm going to factor this out front. So 1 equals dy dx times, that's going to leave me with a 3y squared, and then this, if I divide out a dy dx, just leaves me with a 1. And then I will divide on both sides by that factor. And at this point, all I have to do is plug in my values from the inverse point, because we're using the inverse function here when we derive. So we're going to be using an x of 3 and a y of 2. This particular slope only requires to know the y value, so I'm going to plug in that 2. And then we simplify. Oh, Miss Wright, what am I doing, you guys? I bet some of you were just yelling at me earlier that I completely just dropped the 3/4 or the 1/4 here, which makes this actually a 3/4. Kind of an important detail. So let's see. That should be 3/4. That should be 3/4. Ooh, Y'all, it's late. It's past my bedtime. Okay. 3/4. Alright. That makes a difference because now we have a 4 in the denominator times 4. So it just leaves us with a 3 plus 1 on the bottom. And so we're getting a slope of 1/4 for the inverse function. So the way you would write your final answer is to simply say that the derivative of the inverse at 3 equals 1/4. So that's method 1 for you. Alright, so let's go try out method 2. This one's actually a little bit quicker. So with this one, we're going to find the slope of the original function at 2 and know that the slope of the inverse function at that corresponding point would simply be the reciprocal slope. So the first thing we'll do with method 2 is find f prime of x. Okay, actually let's rewrite the original function real quick. So f of x equals 1/4 x cubed plus x minus 1. So let's find that derivative, which would just be 3/4 x squared plus 1. And now I want to find the slope of the original function at 2. So I'm going to find f prime of 2. And this probably looks familiar. So we're doing 3/4 times 2 squared. The 4's will just cancel out and leave us with 3 plus 1, which equals 4. So the derivative of the original function at 2, 3 is 4, meaning that the slope of the original function at that point is 4. Okay, so to find the slope of the inverse function at 3, which will be at the point 3, 2, since they get switched, will simply be the reciprocal of that function. And I'm going to make you practice the fancy notation. It simply means 1/f prime of 2, which is, of course, 1/4. So using both methods, we were able to get the slope of 1/4 on the inverse function at 3. So let f of x equals 2x plus cosine x. Find the derivative of the inverse function at 1 using both methods. So again, just remember, if they give you this setup at the beginning, the value they're using for the inverse function corresponds to the y value of our original function of that point. So I always start there, because we have to start with either x or y. They have to give us something. Sometimes they're really nice and give you both, but okay, so if y equals 2x plus cosine x, and we have a y value of 1, I'm going to plug that in. Again, I'm going to use a calculator here. Please make sure you're in radian mode. We will never be in degree mode. So again, you're going to use the calculator. You can type one of them into y1, one of them into y2, and then go find where they cross. And for this particular function, they happen to cross at 0, 1. And so that means that's the actual point on the original function that we're looking at, which means that we will be using the point 1, 0 for our inverse function. Alright, for method 1, and I guess we could label that step 2 if we wanted to. So for method 1, we're going to actually find that inverse function first. So if we start with y equals 2x plus cosine x, we're going to have to find the inverse function by switching, which I'm going to be very careful about this time. So 2y plus cosine y. Then we're going to derive it implicitly. So that'll give me 1 equals 2 times dy dx plus The derivative of cosine is negative sine y times the derivative of that inside function, dy dx. We're going to factor a dy dx out front, and that would leave us with 2, and I'm just going to change this to minus sine y. And I'm going to divide on both sides by that factor. Okay, and here we just need to make sure we're plugging in the right value. So since we're using the inverse function to find this slope, we're going to use the point on the inverse to plug in values. So for this one, we just need the y value of 0 to actually find the slope there. So 1 over 2 minus sine of 0. Okay, so that's going to be 1 over 2 minus 0. Fun. Which is just going to be 1/2. Okay. And remember, our final notation would be that the derivative of the inverse function at 1 equals 1/2. Okay, because again, it's saying the derivative of the inverse function at an x value of 1, and we found that to be 1/2. So now just a quick run through method 2. Okay, just gonna put that down the middle. So for this one, we find the derivative of the original function. So just as a reminder, the original function again is 2x plus cosine x. The derivative of that, and we don't have to use implicit differentiation for that, this particular method. So derivative of 2x is 2, and then minus sine x. Then we find the derivative, or the slope, of the original function at the original point, so plugging in a 0 for x. So f prime of 0, again, we just talked about how sine of 0 is just 0, so that basically goes away, and we get that the slope of the original function at 0 is just 2. Therefore, the inverse slope at the inverse point, 1, 0, is going to be the reciprocal of that, or 1/2. And we are done. So you'll be able to use whichever method you prefer on any assessment, but we will be practicing both during the classwork. This concludes our notes on finding the derivatives of inverse functions.